hadirin yang dihormati sekalian, salam sejahtera. Dengan sukacita saya berada di sini, ingin berkongsi mengenai teknologi hijau viola yang boleh diaplikasikan kepada pembangunan bandar-bandar lestari di Asia. Semoga segala ilmu, pengetahuan, pengalaman, dan kepakaran yang dikongsi bersama menerusi webinar pada hari ini memberi manfaat dan kebaikan bersama kepada kita semua. Distinguished guests, ladies and gentlemen, I'm much honored to be here to share with you a topic named Building Sustainable Cities in Asia with Smarter Water Management. The content of the presentation is the following. We start with water recycling and reuse technologies fixing water scarcity, followed by sludge treatment and management. Sludge treatment is very important today for a city, as sludge generated by a wastewater treatment could make a disaster and make a second pollution if not treated properly. But today, sludge is no more considered as a waste to be discharged or landfilled. Sludge can be converted into green and renewable energy. It can be converted into material and resources. I would profit this opportunity particularly to mention a process called thermohydrolysis process, or THP, which is pre-treatment of sludge digestion process. With THP process, we can have a big increase in biogas generation, energy recovery. And finally, stormwater treatment. As you know, stormwater can make a big disaster for a city, but a good management and a good treatment of stormwater can be very important. Stormwater also can be considered as a non-conventional water source. Let's start with the first subject, tackling water stress with water recycling and reuse technology. The global water stress situation is the following. There are 7 countries home to 1/4 of world's population face extremely high level of water stress. These countries are mostly in India, in Middle East, for example. So in these countries, people withdraw more than 80% of the available supply on average every year. And then after 17 countries, there are 14 countries home to 1/3 of the world using more than 40% available supply. This slide summarizes causes or drivers and circumstances. For example, global warming will result in unusual severe drought. Urbanization would make a rising urban demand. Population growth will have a rising agricultural demand. Island economic development will have a consequence of seasonal shortage on islands. Industrial growth will have over-extraction of water in water scarce areas. And over-extraction also can result in seawater intrusion, make the aquifer salination. So to overcome these circumstances, there are 3 possibilities now. The first is a conventional method and the conservation of water resources. And also, we can use reused solutions and desalination solutions. So this slide shows since 2017 and to 2022, reused water market, how it is increased. So in the Americas, in 5 years, reuse market increased by 20%, and the same for Europe and Central Asia. And for Asia Pacific, This increase is more than 50%, and in the Middle East and Africa, this increase is around 30%. Treated wastewater from a wastewater treatment plant is considered reliable and cheap water source for reuse. Water is far too precious for being used only once. Treated wastewater needn't to be directly or simply rejected in the nature because it could be recycled to an alternative resource. When we do the alternative water resource, we can treat the treatment can meet the target. In this way, we can extend the water life cycle and resource preservation. This is a typical scheme of water life cycle extending. So wastewater discharged from a city is treated in a wastewater treatment plant. Based on that, we introduced a reuse treatment plant. Reuse water meeting the reuse quality target is recycled in the industry and other users. Used water is further treated to meet the discharge standard. We can also move forward. We can create multiple loop of water recycling and reuse the water. Reused water is water used more than once for multiple purposes. In this way, we can have water reuse optimized. Reused water can be applied in different fields, such as urban reuse including recreational field irrigation, golf irrigation, landscape irrigation, firefighting, toilet flushing, cooling tower, district cooling tower, and water fountains. In agricultural reuse, it can irrigate food crops, food processing, and non-food processing irrigation, livestock watering. In environmental reuse, it can be used for wetlands, aquatic habitats, river, lake, flow augmentation, groundwater recharge, sea barrier, impoundment, snowmaking, fishing, boating, and swimming. And portable reuse can be used for indirect portable reuse. Now, today, the water treatment process is so sophisticated that we can convert wastewater directly to the potable water. We have a case study in Africa. And indirect potable use is widely used. For example, Singapore New Water, part of New Water is reused as indirect potable use. Finally, industrial reuse. Industrial reuse can be in cooling towers, boiler water makeup, produced water from oil and natural gas operations, steel production, high technology water reuse, processed water, prepared food manufacturing. Now we need to talk about the regulations, which target we need to meet for different applications. Here we have a regulation in France, in USA, and in Southeast Asia, namely in Singapore. So in France, there are 4 categories. The parameters including suspended solids, so suspended solid in treated water, and organic carbon pollution indication in treated water, and then bacterial parameters in its concentration and in its log removal. So in regulatory requirement in the USA, there are 7 applications, such as urban reuse, agricultural reuse, impoundment, environmental reuse, industrial reuse, groundwater recharge, and indirect potable reuse. So the parameters including pH, BOD, is an indicator of organic carbon pollution. Suspended solid represented by TSS and turbidity, and then bacteria in a concentration. And finally, we need to do the disinfection. So it's the residual chlorine concentration. And finally, for the indirect portable reuse, there's one more parameter called TOC, total organic carbon, which is the indication of organic carbon pollution level in the treated water. And this is a gray water standard in Singapore. So the parameters are nearly the same. pH, color, odor, residual chlorine is required. And the turbidity is suspended solid indication. BOD as organic carbon pollution. And the total carbon, total coliform bacteria, E. coli as bacteria parameters. And if it is used in cooling water, we have added a total Legionella count concentration. So this standard is widely used in Southeast countries when we have project reuse water project. So available technology in the market are 2 categories and 3 solution packages. Talking about two categories, the first one is desalination technology. The second one is reuse technology. So in the desalination technology, there are thermal technology is a evaporation technology called MSF MED or vapor compression evaporator. These technologies are widely used in the Middle East for seawater desalination. Other desalination for pollution such as ion exchanger, electrodialysis, and EDI, electrodeionization. And reverse osmosis belongs both to desalination technology or reuse technology. So within the reuse technology, we can easily think about biological treatment. So all biological treatment putting together, such as activity sludge, SBR, MBR, trickling field, biological contactor, moving bed, biological reactor. So moving bed bioreactor is called MBBR. MBBR is what we are promoting strongly in Southeast Asia and also in China. This is considered very good technology. I will present a little more detail later. Adsorption to remove the micropollutant if we have very high water quality, reuse water quality required. So we use activated carbon, granular ferric oxide, and activated aluminium. So adsorption process. And filtration process is widely used like microfiltration, ultrafiltration, media filtration, automatic self-cleaning filtration, and disk filtration. And finally, we need to do the disinfection. Facing very stringent discharge standard in bacteria parameter, we need to go with 2-stage disinfection. That means UV plus chlorination to guarantee very, very low bacteria parameter. Then 3 solution packages according to what we receive as low water quality and what's the final purpose for reuse. We can propose three packages. The first package is called polishing tools. The second is disinfection tools. And the third one is micropollutant treatment tools. So here is the table summarizing different kinds of technology. On the left column, you have a conventional treatment process. We call it secondary wastewater treatment process, followed by three barrier we call the tertiary treatment. So we have first barrier, second barrier, and the third barrier. So with each barrier, secondary treatment followed by third barrier, you have a water quality. And then if you add a first, second barrier, you have water quality improved. And finally, if you have a first, second, and third barrier, you have the highest water quality. So as a reminder, secondary treatment are mostly biological treatment. It can also be clarifiers like lamellar clarifier, ballast flow clarifier, and also a series of BAF biologically aerated filter in addition to the conventional filter. And as first barrier, you can have a clarification technology. You can have microfiltration, ultrafiltration. You can have the disc filter. As the second barrier, you can is mainly remove the micropollutant. So in this case, we use active carbon technologies, and also we can use the ozonation process, and also we can use nanofiltration, reverse osmosis filtration. And the third barrier is the disinfection tools, as I mentioned, for the reuse purpose. Very often we need to go with two-stage disinfection. So Veolia has all over the world more than 400 references spread in 17 countries. The references are located in Southeast Asia, for example, TRX project in China, in Ireland, in Qatar, in Disneyland Paris, and Namibia, Africa. I would particularly mention two case studies in Southeast Asia. So the first one is TRX, located in Kuala Lumpur City. So the full name is Tun Razak Exchange. The objective and the challenge is minimizing water consumption. This is a KPI as a sustainability driver. So along with effort to better wastewater treatment practices, TRX City decided that all buildings would use water efficiency fitting to further reduce demand, and all non-potable water could be supplied with recycled water. So recycle reuse capacity is 100%, and the treatment capacity is 13,300 cubic meters per day. The targeting better than 98% network efficiency, and is LEED Green Building Gold certification, and the first GBI Platinum certification in Malaysia, and the first fully integrated commercially clean water project in Southeast Asia, and a global reference for sustainable development. So looking more into a little more into the detail, the process line is based on the conventional water treatment, but using the compact solution. So the biological treatment part is called moving bed bioreactor. In combination with the lamellar primary settler and MDBR process, the footprint is 5 times smaller compared to the conventional activity sludge. And the blue parts are treatment steps for the tertiary treatment, aiming to get the reused water quality. So these are disc filter for the separation of sludge with treated water, dual media filter to further remove the suspended solids, and two-stage disinfection to meet the bacteriological criteria, and the treated water is 100% recycled. As a sludge treatment line is gravity thickener, sludge dewatering, and dewatered sludge moves to the landfill. Treated water standard is mainly based on the Singapore gray water standard, but the standard is more stringent because we introduced ammonia nitrogen less than 2 milligram per liter, nitrate lower than 10 milligram per liter. Because of the constraint on the nitrogen removal, we have intensive biological treatment using MBBR process, and the rest parameter complying with gray water quality. So this project TRX is under commissioning. The second case study is located in Bangkok, Thailand. It's a project similar to TRX, but with smaller capacity, 10,000 cubic meters per day. The difference with TRX, in addition, we do the 100% water reuse. We have also rainwater harvesting facility. So rainwater is harvested to increase the recycled water capacity. Recycled water capacity is also first lead neighborhood development platinum certificate in Thailand. Going more detail into the treatment process. So the gray part is a conventional treatment process. Also, we use the lamellar primary settler followed by MBBR process. As I mentioned, this process offers 5 times smaller footprint compared with, because this treatment plant is fully underground. Fully underground construct in 3 levels, -3, -2, -1. So we need a very, very extremely compact technology. Here we use dissolved air flotation as a separation process for treated water and suspended solid. And then after that is dual media filter polishing and 2-stage disinfection with chlorine disinfection, UV disinfection, chlorine disinfection. Effluent tank is recycled, including toilet flushing, including district cooling tower recycling, makeup water. So sludge treatment line is quite simple, the same sludge dewatering and goes to landfill. Treated water standard is also we introduced the very stringent ammonia nitrogen, which is 0.5 milligram per liter instead of 2 milligram per liter in TRX. So this is very stringent. We have also to implement a very intensive biological treatment process with MBBR technology.
My SAJ smartphone app. Download now on App Store and Google Play.
So moving forward to the second topic, sludge treatment, circular sludge management, harnessing biomass energy from your wastewater and sludge discharge. Let us remind together the progression of sludge management. Around 1970, we satisfied with the sludge direct disposal to landfill. And from 1990, we start to use the sludge as fertilizer. We spread the sludge to the field and to the landscape. So use the sludge as fertilizer without having very stringent regulation. And from the year 2000, we started to do the sludge to energy, started to produce the biogas and sludge to make green energy recovery and also heat recovery. From 2010 and 2011 and to nowadays, we started to to do the intensive green energy recovery, and also we start to do the material and the resources recovery. So this is where we have today. We do a lot of things on the sludge. And for the sludge treatment roadmap, digestion is at the heart of the process. The digestion can have a pre-treatment upstream digester. The process is called thermal hydrolysis, or THP. So I will profit this to present more in detail THP process. But coming back to the roadmap, so sludge digestion system will receive sludge from wastewater treatment plant generated from wastewater plant, and some sludge is suitable to recover the plastics called bioplastics. And during receiving the sludge from wastewater treatment plant, we can receive also bio waste, municipal solid waste, industrial food processing solid waste. So when we combine two sludge together, it is called co-digestion. So co-digestion will improve greatly biogas production. So what we do is produce the biogas. First thing is that we send the biogas to the cogenerators, CHP system. So cogenerator will produce electricity. So electricity can be sold to the electricity grid. In Europe, thanks to the incentive, green energy incentive, you can sell 2 times more expensive. Then you can buy the energy 2 times cheaper. So this incentive is very interesting. You can make money. So while CHP is producing electricity, it generates the heat. So heat can be recovered to heat the digesters, and also can be sent in form of hot water to urban heating network. Second application of biogas is to purify the biogas. To purify the biogas, the purified methane can be injected to the gas network, gas grid. Then again, you can sell 2 times more expensive than what you buy from the network, thanks to the energy incentive policy in Europe. And also, you can compress the methane. You can fuel the car with biofuel. So this is the quality purified biogas is similar to natural gas. Then digest sludge, what we can do? We can further do the sludge treatment. We can producing the fertilizer by a composting process. We can also directly send to agricultural reuse. We can make a further dewatering with drying process, and also we can make the solar drying at very cheapest cost. And this dried sludge can be used as fuel. Of course, generated sludge can be incinerated directly by special dedicated incinerator. So the ash can be reused for material construction and road construction. And finally, sludge digestion after dewatering generates the liquid. So the liquid is called the supernatant. It's very rich, supernatant, very rich in ammonia. We can also recover we can produce the fertilizer. The fertilizer is called struvite. Struvite is very good fertilizer for agriculture. So now move on to the thermal hydrolysis process. Thermal hydrolysis looks as it is shown in the photo. It looks quite complicated, but it is very easy. Just think about a pressure cooker in your kitchen. So pressure cooker sludge is put in the high temperature as high as 165 degrees with retention time 30 minutes, slightly longer when you cook the meat. And the pressure 7 bar, slightly higher than the kitchen pressure cooker. And then after this treatment, sludge characteristic is changed. Sludge has lower viscosity. Lower viscosity meaning that sludge can be fed at a higher solid, 2 times higher concentration for the downstream digester. And also, when the sludge is cooked, there's improvement of sludge biodegradability. So you have higher biogas production. And you have hydrogenization of the sludge because it is treated at high temperature, 165 degree. Then you have 6 log pathogen removal. And finally, you have better dewatering property. You have get higher dryness. So sludge volume is finally reduced. So let us summary THB combination with downstream digester. You have some advantages. Sludge is fed with much higher, 2 times higher concentration, and retention time is reduced. That means the downstream digester you can design 2.5 times smaller. So digester design is very cheap. And the fed sludge is very hot, so you don't need to heat the digester. And it operates at 38 degree instead of 35 degree, and you get 20 to 30% more biogas produced. So more biogas produced, more energy recovered. So you have a lower capex for digester construction. So this slide shows how sludge volume is reduced. This is the conventional dewatering process. You generate 18 ton per day, and if you do with digestion, you get 17 ton per day. If you do thermal hydrolysis followed by digestion, finally you get 69% sludge volume reduction compared with simple digestion, and you get 44% volume reduction compared with simple digestion process. And this slide shows you have cell lysis, making the biomass more soluble and more biodegradable. This slide shows with the same dry solid 15 to 16%. One is solid pastry state, another is very liquid state. So proving we can feed the digest with 2 times higher concentration. So in the market, Veolia can propose 2 types of packages standard products. The first one is called Biodilis, is a batch reactor. The second is a continuous reactor. So this one, Biodilis, is suitable for meeting as a larger capacity. And XLIS here, I would like to mention you 2 case studies. One case study with XLIS continuous thermal hydrolysis in Billund City, Denmark. So Billund, in this city, when you visit this biorefinery plant, don't forget to drop by legal land. So here in Billund, you have original legal land, and then you have today Johor Bahru legal land. So don't forget to drop by. Legal land is also interesting in addition to XLIS plant visit. So after construction or integration of the XLIS, we have biomass treated plus 110% more, and we have biogas output 130% more, and then you have 10% more organic fertilizer, and the power generation is multiplied by 2.5, from 2.7 gigawatt hour to 6.8 gigawatt hour. So the second case study is with our batch reactor, Biodilis reactor. The plant is much bigger in scale. I participated in the construction design of this plant when I was working in Veolia headquarters something like more than 20 years ago. This plant started more than 20 years ago. Toulouse, the city is called Toulouse, and the wastewater treatment plant is called Gines 2. So Toulouse is the headquarters of Airbus. The city is manufacturing Airbus planes. Is the fourth largest plant in France. So the interesting thing is that with the increased forecast sludge volume by 1.3 times, and while sludge incineration capacity cannot be increased, that means 8,000 tons per year. So the client need to review the existing sludge incineration facility. So today's the situation is dewatering plus direct incineration. And finally, the final choice is thermal hydrolysis biodiesel is introduced in front of upstream sludge incineration. So we will make the enormous 57% sludge volume reduction, meeting 8,000 tons per year incineration per year. So the facility is under construction. Another showcase is that produced biogas is purified by our internal process biogas purification. So all the purified biogas is injected in the natural gas grid. So of course we sell to 2 times more expensive. So the economy, the saving generated, the revenue generated is 4 million euro per year, equivalent to 29 gigawatt hour per year. And thanks also to the introduction of thermal hydrolysis, we get 12% more biogas production. And the steam needed for thermal hydrolysis is from steam recovered from during the incineration. So it's a very nice, beautiful showcase. So here is the diagram. Thermal hydrolysis goes to mainly biological waste sludge. Thermal hydrolysis then mixed with primary sludge, phase 1 going to digestion, and then going to existing incineration. So here is the diagram showing most important thing here is digestion. Produced biogas is purified, producing biomethane, and then digested sludge, digested liquid supernatant going to Anamox process, our in-house process called Anitamox. And then during the incineration, there is not only we have ultimate sludge volume reduction, but also we have energy recovery in form of steam necessary for the THP thermal hydrolysis requirement. So going to the final subject, stormwater treatment and management. The photo showing behind is a stormwater treatment in the biggest wastewater treatment plant in Paris, city of Paris. The plant is called Ashia Wastewater Treatment Plant. The treatment capacity is 30 cubic meter per second, equivalent to 2,600 MLD capacity. This plant is placed during the dry weather in series with existing biological treatment plant, while during the storm event, it is put in parallel because during the storm event, we will receive 2 times more flow. With the additional flow cannot be treated in biological. So what are the characteristics of stormwater? Stormwater is uncontrolled arrivals. You cannot difficultly forecast, and hydraulic and pollution load big variation is located in urban area. So urban area has land footprint issue. So our solution is proposing our active flow. process is called sand-ballasted high-rate clarification technology. Active flow can be placed individually together with a stormwater storage tank, and also can be placed in a wastewater treatment plant. So active flow meets the constraints. It will offer rapid startup, stable performance, and reduced footprint. This curve shows you after 20 minutes startup, the treatment performance becomes normal. This curve shows the pollution and the flow, big variation, and the treated water performance is always stable. So as I mentioned, the treated when active flow is placed in a wastewater treatment plant, it can be used as a tertiary mode during the dry season, and it can be used in parallel CSO, combined sewer overflow. In parallel, the mixed flow treated is discharged to the river. So here I would mention you a case study is located in the city of Lille. So Lille is the largest city in North France. So the treatment plant is called Marquette Les Lille, is the biggest plant in the city of Lille. This treatment plant, water treatment line, adopted a very sophisticated treatment line, MBBR process. So MBBR process combined with activity sludge. We call it IFAS in the market. So we put the media in the activated sludge, offering 2.5 times smaller footprint. And also in the sludge treatment, we introduced the thermal hydrolysis process, XLS continuous process. And this water treatment plant is equipped with a stormwater treatment facility. So the treatment capacity is 700,000 cubic meters per day, equivalent to 620,000 population equivalent. And with the water treatment line has capacity 256,000 cubic meters a day, while stormwater treatment line is 457,000 cubic meters per day. So sludge treatment adopted digestion, thermal hydrolysis digestion. So this plant, wastewater treatment plant, is a real example of wastewater plant for the city of the future. If you have opportunity, it's very nice to visit this plant for the city of future. So treatment line is, as I mentioned, water treatment line based on the MBBR primary treat MBBR process. The extra flow, which cannot be accepted by the treatment plant, is diverted to our stormwater treatment facility. So there are 3 active flow facility. And for the sludge treatment, you have XLS thermal hydrolysis and digestion, and also sludge drying. So here is the outcome of the stormwater facility. So now is operated since 4 years, and it's designed at very high velocity, 100 meters per hour. So this facility is very compact. It's 5 times smaller compared to traditional high density setting technology. The performance reaches expected performance, BOD 60 to 75%, COD 60 to 75%, suspended solids 80 to 85%, and the total phosphorus 70 to 80%. So produced sludge can be introduced to either thermal hydraulic digestion system and also can be dewatered directly. But this primary sludge offers higher dewatability with 30% dryness. So finally, as a conclusion, climate change may result in more severe water scarcity all over the world, Veolia has always been committed to provide low carbon footprint and sustainable development solutions. Veolia is committed to resource the world. Water reuse for various applications, renewable energy production with resources recovery, and desalination as well as stormwater treatment and management are key technologies nowadays for a city of the future. Thank you very much for your attention. Terima kasih.